Let's start by making this a little bit smaller because this one is complicated. What are we talking about? Titration calculations, specifically calculating the pH at the equivalence point of a weak acid, strong base titration. It doesn't get much more complicated than this, but let's dive in. So we want to determine the pH at the equivalence point if 50 milliliters of 0.4 molar HF is titrated with 0.5 molar NaOH. First thing we need to do is write out the neutralization reaction. And yes, I chose HF on purpose because I want you to remember that it is a weak acid. HF is a weak acid, not a strong acid. Anyway, we're titrating that. We are forming water and then our conjugate base, sodium fluoride. Why is that conjugate base so important? Because at the equivalence point, we have equal moles of our acid and our base. What does that mean? We have our conjugate base in solution, and that is what is going to determine our pH. So now what we need to do is we need to determine the volume of sodium hydroxide needed to reach the equivalence point where we have equal moles of acid and base. Because it is just a 1-to-1 ratio, you can basically use the dilution equation where we're just solving for the volume of the base, which is going to be 40 milliliters. Alternately, you could also just calculate the moles of your acid and then work backwards to solve for the volume of your base. Either way, you'll get to the same answer, 40 milliliters. Why do we need this again? Because we now need to find the concentration of our conjugate base. To do that, I'm just going to set up a quick BCA or before change after table where I'm just looking at the moles. So I calculate the moles of acid. Those are equal at the equivalence point. I'm assuming I have none of the conjugate base initially, and then I'm going to end up with 0.02 moles of my conjugate base. So now I'm going to take that, the number of moles, divide by the total volume of the solution, which was 50 plus 40, so 0.09 liters, to get my concentration of 0.222 molar. All right, so we are off to a good start. We've written out our neutralization reaction. We found the concentration of our conjugate base. Now we need to determine the Kb, or the base dissociation constant. So to do that, you have to remember Kw is equal to Ka times Kb. Kw and Ka are just given constants. So for hydrofluoric acid, it is 6.8 times 10 to the negative fourth. We'll use that to find our Kb value. This is assuming we are doing this at a temperature of 25 degrees Celsius, because remember, any of those K values are temperature dependent. You're like, okay, what's going on now? So we have to remember we're looking at our conjugate base in solution with water, and we're basically looking at the reverse reaction. So if I set up my Kb expression, or my base dissociation constant, it's going to be equal to the concentration of hydroxide times the concentration of the conjugate acid over that initial weak base, or my conjugate base. So I could set this up as x squared over that concentration of my conjugate base, which I just calculated, and then I'm just going to solve for x. But I have to keep in mind, like, why am I solving for x? Because x is equal to the hydroxide, the OH minus concentration. So in this case, it's going to be 1.81 times 10 to the negative 6. I can then remember POH is equal to the negative log of that OH minus concentration to find my POH. And we are so close to finding that pH now. So now all I have to do is just remember that 14 is equal to the POH plus the pH. You are simply subtracting in this very last step of this complicated titration calculation to find out that the pH is equal to, let's see, drum roll please, 8.258, which makes sense. It should be above 7 because we are working with a strong base. I hope this was helpful. As always, please put your requests for my next video in the comments.